Howdy, today is August 20th, Thursday, and we are taking a look at inverse functions. We dabbled with them a little bit earlier in the semester, and we're going to take a little bit deeper look into them now. And we're also going to look at another function known as the identity function. So let's get started. And by the way, if you're wondering, this is a beautiful New Mexico background. This is around Santa Fe, which is my old hometown. Alrighty, so identify the relationship between an identity function and the inverse function. So first of all, we got to talk about what is an identity. Alright, an identity is when an identity is applied to something, it doesn't change it. For example, if I asked you, if you took the number 5, what would you add to 5 to leave it unchanged? Well, 5 plus what is 5? Well, the answer is 0. So 0 is known as the additive or the addition identity. That's 0. Okay, if I asked you, okay, what's the multiplication identity? So now you're thinking, well, what could I multiply 5 by so it doesn't change it? Well, that would be 1. Okay. So my multiplication identity is the value 1. So identities don't change things. So what we're looking at now is what a function identity is. Alright, so let's say you had the function f of x equals x plus 3. Alright, what function could I compose with it so that it would still remain x plus 3? Okay, when that function that I compose with it is called the identity function because it's not going to change it. Just like adding 0 to 5 didn't change it. Multiplying 5 by 1 didn't change it. Okay, now we're looking for a function that does the same thing. All right, don't let the notation confuse you here. This is very, very simple. It's just understanding how things get substituted. All right. So we're going to say let the identity function be some function and we're going to call it I. So Ix represents this thing that we can compose with f and not change it. Alright, so here I'm doing my composition, f composed with I. Alright, if I did that, I can rewrite that as f of I of x. Okay, this is no different than what you've been doing with composing f and g. Okay, when we did that, we learned that is the same as writing it like this. Now all I'm doing is using an I instead of a G. Okay, now what we want to happen is this. This right here is the composition. And when it comes out of that composition, we want it to be the same as when it went in. So it's equal to the same thing as it was before. It didn't change. It's still f of x. All right, in order for that to happen, all you got to do is ask yourself, what would this have to equal so that when I put it in there, it's an x? Well, it would have to equal x. If Ix is the same as x, then what that means is I can take this out and I can replace it with an x because those two things in green are the same. So what that does, it keeps f of x the same. It's still f of x. So the identity function is I of x equals x. Now people always get that, it's confusing sounding. It's really just this, watch. y equals x is the identity function, or f of x equals x is the identity function. Those are these two things are the same thing. Okay, I just used the letter I so that we would know, okay, that's the identity. Okay, and some textbooks do that. All of those are the same thing. So when we talk about identity functions here, as we move through this lesson, really the way I want you to think about it is when you think about the identity function, just think about the equation y equals x. Okay, that's what the identity function is. Okay, so let's try it here. I'm going to take f of x, and I'm going to let I of x equal x. Okay, and I'll show you that when we do this, we end back up with x plus 3. It doesn't change. All right, so I'm going to take f, and I'm going to compose it with I of x. Now, because I of x is the same thing as just a plain x, I can take this out, and in its place, I can just write an x, because these two quantities are the same. All right, well then, what's f of x equal to? X plus 3. So we composed f with the identity function, and it didn't change. That's what an identity function does. So f composed with the identity function is unchanged because it just stayed x plus 3. So that's what the identity function. So we're in New Mexico. New Mexico's from where Billy the Kid ran around, and so I put it in a wanted poster. Wanted, what's the identity function look like? Well, a few minutes ago, or a few seconds, I just told you that the identity function is the same as y equals x. All right. Whatever the x coordinate is, the y coordinate is the same. So 3, 3, 2, 2, 1, 1, 0, 0, -1, -1, etc. It's just a diagonal 45-degree line. That's what the identity function is. All right. The identity function also goes by a couple aliases, f of x equals x or y equals x. So that's what the identity function looks like. Okay, now that we've identified what the identity function is, we're going to take a look at a different type of function that's related to it that is known as the inverse function. All right, think of the word inverse like reverse. What an inverse function does is it reverses the action of a function. The notation that we use to represent an inverse is f with a little exponent of -1. So when you see that, you read it as the inverse of f of x. All right, so let's see how an inverse reverses the action of a function. So I've got a pretend function here. This function f takes apples and it changes it into lemons. So apples go in, lemons come out. So the inverse function of f would take lemons and change them back into apples. That's what an inverse function does. It reverses the action of the original function. Now there's some important relationships about the domain and the range of a function and its inverse. And we can discover that by using our apples and lemons. All right. What goes into f is known as the domain of f of x. So what we put into the machine are apples. That's my domain. All right. Now, what comes out of this first machine is called the range of the original function. Well, the range of that function, the lemons, becomes the domain of the inverse because they're going into the inverse. So lemons are two things. They're one, the range of the original function f, and they're the domain of the inverse function f negative 1. What comes out of f negative 1 is the range of the inverse. All right, now I color-coded these to show you that which ones are the same. All right, let me use a highlighter here. Okay, so the domain of the original function is the same as the range of the inverse. See how they're both apples? So that's what I said right here. The domain of the function will be the range of the inverse. Now, at the same time, the range of the original will be the same as the domain. They're both lemons of the inverse. So what happens is the domain and the range of the original, okay, become the domain becomes the range of the inverse, and the range of the original becomes the domain of the inverse. They switch. All right, I'll draw a little picture here to show you that. All right, so when you hear all that domain and range, it can get confusing. So if I take the domain of the original function, it's going to be the same as the range of the inverse. That's these two parts that I highlighted in green. Okay, the range of the original function is equal to the domain of the inverse. That's the two ones that I highlighted in purple. And that's an important concept to know about inverse functions. Because later on when we decide, not all functions have inverses. Okay, so we use that property later on to figure out which functions have inverses and which don't. All right, so here's another example. Now I've just made it an algebra example. Okay, the range, okay, so we've got a function f of x, and it's x plus 3. All right, so what it does is it takes its input, so its inputs are 2, 4, and 11. And what it does to them is it adds 3. So the 2 turns into a 5. Okay, the 4 turns into this should be a 7, not a 4. And this 11 turns into 14. That's what the function does. So if I wanted to reverse adding 3, it's pretty intuitive that I would subtract 3 and I'd be back where I started. That's what the inverse does. So here the inverse, when it goes into this box, it takes away 3. So it takes that 5, turns it back into a 2, okay, takes the 7, turns it back into a 4, and takes the 14 and turns it back into an 11. That's what an inverse does. So what happens is you're back with the same values you started with. You reverse the action of the original function. Kind of like, I guess, going back in time. All right, so if you look at a set of ordered pairs, if I want to take if I said write the inverse of this function, and the function is a set of ordered pairs, well, to write its inverse, all you got to do is take the x and y's and switch them. So 2, 5 would become 5, 2. 4, 7, 7, 4, 11, 14 would become 14, 11. That's how you get an inverse. Take the coordinates, and flip them. So here's an example of that you would see on your Math Excel. Determine whether the following statement is true or false. If the statement's false, make the necessary changes to produce a true statement. Okay, the inverse of 4, 6, 5, 7 is 5, 7, 4, 6. So, true or false? Well, hopefully you said false, because all we did here was switch the order of how I wrote them. We didn't switch the x and y coordinates. So this statement up here is false. The true statement would have been taking 4, 6 and writing it as 6, 4, taking 5, 7 and writing it as 7, 5. That now, this is the inverse of this relationship. I switched the x and the y's. All right, so if you had a table and I said, use this table to write the table of the inverse. Well, to do that, you switch x and y's. So remember, f of x is the same as y. So all I'm going to do is switch these. 12, negative 2, 6, 0, negative 6, 4, negative 12, 6. And now the second table is the inverse of the first table. That's inverses. I've reversed the action. I've reversed the mapping. All right, the next thing to understand is what's the relationship between a original graph and its inverse graph? How are they related to each other? So up here on the screen, the blue graph is the original function. The black dotted line here, this is the identity function. And then this red function is the inverse. X plus 3 is undone by x minus 3. Okay, so what do you notice? Well, if we look at these two graphs, all right, the inverse is the reflection of the blue graph in the line y equals x. All that means is if you took a point on the blue graph, let's say I took this point right here, which is 1, 4. Well, when I reflect that in the line y equals x, all I do is take it and switch the x and y coordinates. So the point 4, 1 is on the graph of the inverse. And then I usually check another one, okay? That's the point negative 3, 0. So that means 0, negative 3 should be on the inverse, and it is. So that's how graphs are related. So if you have a graph, if you think about it this way, and you fold the paper along the diagonal, fold it over, what you would see is the inverse function. That's what it looks like. Okay, so the important thing to know here is when you see the instructions reflecting the function in the line y equals x, all that does is it swaps x and y. It switches them. So if 1, 4 was on the graph, it would become 4, 1. So earlier in the lesson, the question at the very beginning was, what's the relationship between an inverse and the identity function? Well, the inverse is the reflection of the original over the identity function. If xy is on the original, then yx is on the inverse. All right, so we're going to graph by hand a function and its inverse, and then I'll show you a really easy way to do it on Desmos. So I want to graph f of x equals 2x plus 3. So that has a y-intercept of 3. Let's do it in blue so it matches that. Blue, okay, there's my y-intercept. And then a slope of 2. So that's 2 up, 1 right, 2 down, 1 left. And then I would draw that line. If I'm going to graph this by hand, then all I do is take 2 points on here and switch them and connect the dots. So for example, here I got, let's see, 2, 7. So I'm going to plot the point 7, 2. Okay, I have the point on the original that is 0, 3. So on my new graph, my inverse, I'm going to plot the point 3, 0, and then I'm going to join those two with a line. All right, so I first graphed the line. Then I drew the line y equals x, which is a diagonal line through 1, 1, 2, 2. Then I chose some points on this graph, took the coordinates from it, and reversed them, and then connected the dots. Now, if you're doing it on Desmos, what I did is I typed in the equation, y equals 2x plus 3. Then I typed in the identity equation, y equals x. And then to get it to graph the inverse, all I did was I took the x and the y and I switched them. So this last equation here goes x equals 2y plus 3. And that gives me my inverse. Because what is it? It's switching x and y. It's reversing what the function did. All right, the first few problems in your Math Excel are going to be asking you to verify or determine whether or not two functions are inverses. So what we're going to do is use the identity function as a way of proving that. Okay, two functions are inverses of each other if their composition results in the identity function. So here's the composition. I'm going to take h, put it into g, and then I'm going to do g into h, and each time I do it, I should just end up with x. If that happens, then it's the identity function. Then, excuse me, the two functions are inverses of each other. All right, so I'm going to write up the compositions and be right back. All right, so I put the first composition was h into g. So here's the math, and when I simplify that, I get x. So when I put h into g, I get x. The second one here puts g into h. All right, here's the math. When I simplify that, I get x. So h, the composition of g into h, also gives me x. So each time I got an x for both of these, which means these two functions are inverses of each other. When a function has an inverse, it is called invertible. So g is an invertible function, h is an invertible function. Not all functions are invertible, but that's for the next lesson. So here we have another same question. Are these two functions inverses of each other? So I would pause the video and try to do these two compositions and determine, do you get x each time? And if you do, then they're inverses. So I'm going to write it up and then be right back. Okay, here are my respective compositions, and when we simplify these, those cancel. All right, and so now I got x minus 3 plus 3, and that is equal to x. So it passed the first part of the test. Over here, those 3's cancel, and I have 2x over 2. The 2's cancel, and I'm left with x. Hence, okay, hence just means therefore in the world of IB. Hence means look at what I did beforehand, and this is how I'm making this conclusion. G and H are inverses. All right, this next question asks you to visually determine whether a pair of functions are inverses of each other. All right, so here's what you're going to do. You're going to go to Desmos. All right, you're going to type in this equation. You're going to type in the second equation, and you're going to type in the line y equals x. And then you're going to look at those graphs. Okay, now I already did that, and I just copied and pasted them right here so you could see them. All right, so here's the two graphs that I put in. Then I put in the graph y equals x, and then the second one, 1 over x plus 4. And I want to know, are they inverses? So I took a point that was on f of x. That's the red graph, and that point was 1, 5. Well, I know that if they're inverses, 5, 1 has to be on the other graph. And you can see when you plot 5, 1, it's not on the green graph. Therefore, these are not inverses. And the way that we write it, or we explain it, is we say hence, just meaning, look at the work I did above. G, F, and G are not inverses. Now, if you want to know what the inverse actually looks like, that's this last equation right here. And then I'll show you the graph. So what I did was I took x and y in this equation, and I switched places. And then I graphed it. Okay, and here's what it looked like. So this is, if they were invertible, this is what they would have ended up looking like. Okay, the red and the purple graphs are inverses of each other. And the way I did it, again, I took the one I wanted to see what its inverse looked like, and I just reversed the x and the y variables. And now you can see if I took the test point 1, 5, on the purple graph is the 0.51. That tells me that that's what the inverses would look like. They're going to be the one graph reflected in the line y equals x creates its inverse. All right, the last question, example, you'll see on your Math Excel, it says determine whether a pair of functions expressed as tables are inverses of each other. All right, so we're going to do the composition. Okay, this first table right here, we're putting F into G. All right, so I'm going to take X in F, and it gets mapped to 7. Now that becomes the input in G, which gets mapped to 5. Well, that's good because what we started with is what we ended with. That's what inverses do. Okay, next one, I'm going to take the x value 8. It gets mapped to 2 in function f. And now that 2 becomes the input in function g, and it gets mapped back to 8. That's good. What you started with is what you ended with. Didn't change. That's what an identity does. And when functions do that to each other, that means they're inverses. All right, 6 gets mapped to 3 in F, and then 3 gets mapped back to 6 in G. So the first part works. Okay, I'm sorry, we did this one right here. This is f into g. So that passed. Now I'm going to check the other one. All right, now I'm going to put g into f. Okay, so let's see how this works. So now I'm going to start over on the G table. 7 gets mapped to 5. Then that 5 becomes the input. 5 gets mapped back to 7. Yep, I ended up with what I started. Okay, 2 gets mapped to 8. And I come over here, 8 gets sent back to 2. Yep. And then finally, 3 gets mapped to 6. And I come over here, and 6 gets mapped to 3. So I can say that F and G are inverses. And that's it, folks. So for this lesson, this is the question we started out with, and we learned that the inverse function composed with its original equals the identity function. That's the relationship between the identity function and the inverse of a function. And what your assignment is Math Excel 9, determine if two functions are inverses of each other. And then the next lesson, we actually take a function and algebraically turn it into its inverse. See you next time as you watch the beautiful sunrise in New Mexico. Take care.